We are learning about acids and bases. You can see there's a nice pretty picture here showing that all substances have either a pH of 0 all the way up to 14. Pure water is right in the middle with a pH of 7. Things that have hydrogen ions dissolved in solution are acids, so they have a pH between 0 and 7. The closer you get to 0, the more hydrogen ions are dissolved in that solution. Things that are bases have hydroxide ions dissolved in solution. So the closer you get to 14, the more hydroxide ions there are in solution. Let's look at some definitions of acids and bases. So Arrhenius said acids are things that add hydrogen ions to solution, and bases are things that add hydroxide ions to solution. This was not the best definition to include all bases. It's a good definition and it's true, but there are some bases that don't fit into that. So along came the Bronsted-Lowry definition. The definition for acids is still the same here. Acids donate a hydrogen ion to solution. But here, what's different is it says a base is any chemical that accepts a hydrogen ion into its structure. So basically there are two types of bases. Ones that are ionic and they have a hydroxide in their formula, and bases that are covalent, and these rip a hydrogen ion from water, leaving a hydroxide behind. We're going to draw a picture of this in a second. Both of these bases, though, add hydroxide ions and increase that pH, creating the basic solution. So let's draw a picture here. If I add some sodium hydroxide into some water, I dissolve it in some water. This isn't a reaction, it's a physical change. That sodium gets ripped apart from the hydroxide. The water molecules, because of their polarity, they pull that sodium away from the hydroxide. And notice here, anytime you see hydroxide, you should have a bell go off in your head that says, this has created a basic solution. So if you looked at NH3, you wouldn't say to yourself, oh, that's definitely going to add OH minuses into solution, but it does. So based on the Bronsted-Lowry definition that bases accept a hydrogen, this NH3 rips off a hydrogen from a water molecule, leaving behind a hydroxide ion. So again, this should scream to you, this is a base every time you see OH minus. So there's a little mnemonic to help you out. Bases accept hydrogens and acids donate. So in our little picture here, in this first example, this acid, HCl, is donating its hydrogen to the water. Now it's H3O+, and the Cl is all by itself. Down below it is the example we just did, where NH3 rips off a hydrogen from H2O, leaving behind a hydroxide. Other terms you might hear, the H3O+ should scream to you, this is an acid. It's also called a hydronium ion. And again, OH minus is called a hydroxide. There's a new term here. You've probably heard of people who are ambidextrous. They can write or eat or play sports with either hand because the prefix am means both. Well, amphoteric is a term that means water can act as both an acid and a base depending on the situation. Now keep in mind, water is not an acid or a base. It's neutral, but it can act as either in that it can donate a hydrogen or accept a hydrogen. So let's draw a picture of this happening. So first, I'm going to draw HCl plus H2O. What is going to happen here? This hydrogen is going to be donated to the H2O, so now it's H3O. Again, what should you scream here? We've created an acidic solution because HCl is an acid. It's donating a hydrogen. Water in this situation is accepting a hydrogen, so it's acting as a base. What if, though, I had started with a chlorine ion, and I'm going to draw HOH, H2O, separate it out like that. Now, this water would donate its hydrogen to the chlorine. Chlorine is accepting a hydrogen, it's acting as a base. So we've made, HCl and OH minus. So this should scream to you that that chlorine ion made the solution basic when you see that OH minus. So here we can see that water is amphoteric because it can act as a base or an acid, depending on what it's combined with. Your turn. Which compound here is acting as an acid? Well, don't look at water first. Let's look at the HBr. It is donating a hydrogen to that H2O. So acids donate. So the thing acting like an acid is HBr. Water here is accepting a hydrogen. So water is acting like a base. How about here? What's acting as a base? Bases accept. So which one of these accepted a hydrogen? The SO4, the sulfate ion, is accepting a hydrogen. Predict the products when H3PO4 is added to water. Well, this is an acid. It's going to donate a hydrogen. So we're going to be left with H2PO4, and we made H3O plus. Now this can keep continuing here. So the H2PO4 plus the H2O, it can lose another hydrogen. Now we would be left with HPO4 2 minus, and then it can lose its other proton, its other hydrogen here, and eventually just become a little old phosphate ion, PO4 with a 3 minus charge. Alright, let's talk about some properties of acids. We've been talking a lot about how they're corrosive, they're damaging to your tissue. They taste sour. Think lemon juice or orange juice or grapefruit juice. That citric acid makes them taste sour. They contain hydrogen ions when dissolved in water. You need to know that. They have a pH less than 7. They have all these ions, so of course they conduct electricity. And they neutralize bases. Think about this. If you've got a base spill, okay, you've got something with a pH of 14, if you add acid to it, it's going to bring the pH down to 7, which is neutral. Examples of acids: stomach acid, sulfuric acid, nitric acid, carbonic acid in your pops. You've got uric acid in your urine. Vitamin C is an acid. Citric acid we've mentioned, acetic acid, all sorts of acids. Of course, sulfuric acid is the one, when it's most concentrated, it's 19 molar. That stuff will go right through your skin down to your bone. Just as an aside, this is more of an AP Chem thing, but if you're wondering where the names for acids come from, there's special rules. Like, acids usually have the format HX, and X is some sort of a negatively charged ion, an anion. The name for the acid actually comes from that anion. So if you've got an anion that doesn't contain oxygen, like HCl, you would name it hydro, whatever the ion is, ic acid. So this would be hydrochloric acid. If you had HBr, that's hydrobromic acid. On the other hand, if your anion does contain an oxygen, like HNO3, there's no prefix like the hydro, you just end it in an ic, like nitric acid, sulfuric acid. about bases? Bases, rather than tasting sour, they taste bitter. They're very slippery feeling. They still have ions dissolved in solution, so they definitely conduct electricity. They have a very famous product. Bases plus a fat makes soap. Bases neutralize acids. So if you've got an acid spill, something with a pH of 0, you can add base to it, like baking soda, to bring the pH to 7 so that it's neutral. Bases are also corrosive, damaging to tissue. Examples of bases. We're using sodium hydroxide to make soap. You might have heard of some of these other ones. Ammonium, calcium hydroxide, magnesium hydroxide. They're in things like your antacids that you eat when you've got an acidic stomach. Lots of bleaches, soaps, toothpaste, cleaning agents have bases in them. Now, indicators are beautiful. These are things like cabbage juice or the universal indicator, pH paper. They change color when they're exposed to an acid or a base. They can help tell you if a substance is an acid or a base, even the strength of it. The indicator itself is typically a weak acid or a base. That's what it's made of. Other examples that we haven't talked about: litmus paper. It turns red in acids and blue in bases. And phenolphthalein. We're going to play with that one pretty soon here. It's clear in an acid, it's pink in a base. So, just to recap, an acidic solution is a solution where hydrogen ions, also known as hydronium ions, are winning. There's more H pluses than there are OH minuses. And a basic solution is the exact opposite. There's more OH minus ions than there are H plus ions. A neutral solution is where you have the exact same amount of both. So pure water. And that funny example I gave of the professor that had the 12 molar hydrochloric acid, the 12 molar sodium hydroxide, both would burn him if he drank either alone, but he mixed them up together and he made salt water because he made a neutral solution. pH is something that measures how many hydrogen ions there are in solution. So again, we've got this scale that goes from 0 to 14, 7 being right in the middle, that's neutral. As you get closer to 0, something becomes more and more acidic. As you get closer to 14, it becomes closer and closer, or it becomes a stronger and stronger base. There's just another picture showing some different pHs. Little joke for you, you're a 10 on the pH scale maybe because you basic. Finally, strong versus weak acids and bases. So it kind of goes against what you'd think, but strong acids actually fall apart the most, versus weak acids don't. Only some of the molecules dissociate. So, and this picture's kind of small, but there's a strong acid, or a strong base. All of the NAs are separated from the OHs. And then down below it in the second picture, I guess I can make it bigger here. This is a weak base because a lot of the NH4 OHs stay together and just one dissociated. So that's a weak base. Then, just as a warning for when we're making soap, this is somebody who got acid in their eye and then base in their eye. So you definitely don't want to mess around with this stuff. That's why I'm always preaching to you guys to wear your goggles, because it's for your own safety. And you've probably seen this poster, Carol never wore her safety goggles, and now she doesn't need them. Alright, last little bit if you're interested, a little more practice with acids and bases, like how to identify if something is an acid or a base. Special rules: if it starts with an H, it's an acid. Okay, there are some acids that end in an H, like if you see a carboxylic acid, but most of the time they start with an H. And for our purposes, bases end in an H. Okay, number 18, draw a picture of acetic acid, a weak acid, versus a strong acid. So for the strong acid, remember those dissociate more completely. So you're going to draw the H's separated from the Cl's. And for the weak acid, you might draw some where this whole thing splits apart, but a lot of these are just going to stay together in solution. Identify the reactants as acting as an acid or a base. Don't forget your bases accept a hydrogen and acids donate a hydrogen. It spells bad. Write it out, it helps you. So like here we go, we've got this H is going to H2O, so this is donating a hydrogen. It must be acting as the acid. The H2O now became H3O, so that must be acting as a base. It accepted a hydrogen. Now we've got to predict some products. Always start by looking at the thing that is not water. So let's look at letter A. H2CO3. I know that's an acid because it starts with an H. So it's going to donate a hydrogen. So this would become HCO3 minus plus H3O plus. And it would not be wrong to take this to lose another hydrogen as well, but you don't have to for this. Okay, I'm going to skip, let you figure out the rest. Actually, I'm going to help you with B. I'm going to write out this H2O as HOH because it's a little easier to see. This is donating a hydrogen. It's the only thing that can. So this becomes HClO4 plus OH minus is all that's left. So this is a base and water is an acid, acting as an acid. Let's skip down to letter E. This is a trick one. NaOH plus H2O, people try and combine it with the H2O, but really what happens is that sodium dissociates from the hydroxide and both of those ions are just dissolved in the water. So you don't have to do anything with the H2O. You just separate out the Na and the OH. Alright, hopefully that will